So good morning if you're joining from different part of the world. Good day, everyone. So my name is Hamid Behmanish. With my respected colleagues, Moa and Anna, we would like to have a session on the RTA, latest feature that we implemented in Whitson. So it's going to be fundamentally focusing on the RTA, specifically classical RTA and numerical RTA. And going to be meeting this session going to be held virtually. So Microsoft Team, please everybody keep your mic and video muted during the session. But please, if you have any questions, send it in the chat box. Either myself or my colleagues will be addressing those questions. Over 140 people registered for this session, so it should be exciting and hopefully going to be interactive. So we intended to have 3 hours of presentation divided between some theory and also hands-on practice. And if you have any question, just reach out in the question and answer chat box. So a little bit about Whitson Plus. We have a lot of features. Some of these features are dedicated to unconventional, so like the stuff that we're gonna present today on the numerical and analytical RTA. But there are a lot of other stuff that is really apply to different type of reservoir. So DCA, phase behavior, and some PBT behavior, bottom hole pressure calculation. Any calculation, any analysis depends on the bottom hole pressure calculation. Fluid material balance is also a very great tool that applies to not only unconventional but also conventional reservoir. The numerical simulation is the way it is structured in Whitson. It is applies mostly for the unconventional reservoir, and nodal analysis. There's production engineers and well test. The stuff that so far we have in Whitson is dedicated for unconventional. There's a companion to Whitson Plus, which is Whitson PBT. All the PBT stuff that goes in the Whitson Plus, it's coming from Whitson PBT. So if you're dealing with some complex phase behavior, highly recommend to take a look at the Whitson Plus, Whitson PBT features as well. Just as the one announcement, tomorrow we're gonna have Whitson gonna hold knowledge sharing session. It's mostly people from Whitson and also some folks from industry. It's a great place to see what's the latest and greatest in the industry in the world of unconventionals and also enhancement and feature that we have implemented in Whitson. So please reach out if you are interested to attend these knowledge sharing, and the session going to be recorded. So if you have some other obligation tomorrow, you can reach out for the recording session as well. They're going to be happening. Well, going to happening in for early October this year. Is WISCON is the annual meetings that we hold, and we invite industry folks, and it's kind of SPE kind of events that people from industry come and present their daily cases that they are dealing, their challenges, and how they resolve it. And most of these folks are using Whitson Plus, and we received a lot of great feedback from these, and these are great place for us to elevate and raise the bars for the feature that we already have in our software. And throughout the year, we hold 7 different virtual courses. And today we are in this session, analytical and numerical RTA. And there are a lot of these courses are somehow related. So the fundamental are the same, somehow related. So I highly urge you that don't be satisfied with one of these courses. Try to attend as many as these courses possible. And this course, version of this year is totally different from last year because we implemented new feature. The interface has changed. The software has become more robust. So it's really worth a visit and attending this course. And I recommend it to every each of you. And not only that, but also on the certificate. So we prepare some of these certificates. These are great starting point, not also great starting point, but also a great refresher. So if you are not doing RTA for a couple of months and you're going to get back and see, okay, you're looking for a specific feature, I highly recommend you to take a look at this certificate. Get this certificate as a good motivation to also earn the certificate, but with the purpose of just getting to know the latest feature that we implemented, because the manual and the certificate will be updated based on the feature that we include. So it's dynamically changing sometimes on the monthly basis. So take a look at those certificates and reach out if you have any question. We have a great support team. I hope some of you folks sitting in a meeting today can kind of confirm it. You had experience with reaching out with the support team, and we try to get back to you less than 2 minutes. It's real. It's not the chat box. It's a real human being sitting in their offices, getting back to responding to your emails. We treat every ticket very similar. Any clients are very valuable to us, and every time we try to get back to you as soon as possible. So let's get started on the rate transient analysis. The couple of slides, next slide, I'm going to show you, present to you. It's based on the true story. It's a client that reached out to us and wanted to help them just convince their manager why they need to do the rate transient analysis. And the story starts with, we have been reached out by a couple of folks in the industry, and what they mentioned to us, they have a field development team that they are evaluating for next phase of drilling. And what their current approach is, they favor the location based on 12 months cumulative production. So what they did, they have a couple of places for their field development strategy, and they want to favor the area with the 12 months cumulative production to be their next phase of drilling. And what the manager told the engineers, which is true, it's not made up a story. Let's drill in an area where the well shows 5 BCF in 12 months. So what they did, they presented a bubble map kind of presentation and say this area seems to be more prolific. And therefore, they're going to focus the next phase of drilling in this area, because simply enough, the wells in this area produce more gas, BCF of gas in the term of 12 months. So that's going to be our sweet spot. And the other area that only shows 1 BCF, in this case, seems to be a little bit less productive region here, based on the cumulative at least, is only produce 1 BCF. So we're going to put our next well here. So this was the idea, but what we wanted to put together a couple of slides and help them to highlight the importance of the RTA, and we came up with two important questions. First of all, is the 12-month cumulative is telling us the full story? What if the scenario could be the high early cumulative production, 12-month production, could be a result of aggressive completion in poor rock, or the other way around, we are sitting in a premium acreage, but the well is understimulated. Because at the end of the day, the 12-month cumulative production, combination of the reservoir quality and the completion metrics that goes into completing those wells. So the engineer proposition, what try to help them with is just to do rate transient analysis to decouple two important factors, which is reservoir quality and completion effectiveness. And with that, we presented three examples, and this example, despite the fact that these are cartoons, but it is supported by full physics numerical simulation. So we took two wells in different area, and what we realized that these two wells are not on the same drawdown. So the first step, which looks very trivial, is to make sure that the wells are producing at least similar drawdown. So based on this one, the well number 2, which is exposed to less drawdown, is still producing the same cum after 12 months, similar to well number 1. So definitely be sitting in the better acreage or better completion. So we haven't adjusted for the drawdown, therefore we cannot make a conclusive conclusion about if this is the sweet spot to drill next well. Next one is we selected two other wells, and what we realized, well number 2 has completed as twice number of fracture as well number 1. So the completion metrics for these two wells are significantly different from each other. But both of them has generated the same amount of cum after 12 months. What it's telling me is well number 1 is definitely taking advantage of higher quality premium acreage, rock, permeability, porosity, could be initial pressure, anything. Well number 2 was able to produce the same cum after 12 months with aggressive completion. So we haven't accounted for aggressive completion. So it comes at a different cost and price tag. Case number 3, we have two different wells in different regions. And what we realize, most of the wells have the same number of fractures. But during this 12-month cumulative production, each of these fractures was producing independent of each other, i.e., there's no pressure depletion in the middle of the fractures. So as long as the fractures are producing in the transient linear flow or infinite acting mode, mode, the cumulative is going to be sum of production from each of these individuals. So it doesn't depend on how far they are spaced. So with these three examples, it is a key message of RTA, what we are doing with RTA. Try to qualify and quantify reservoir quality as well as completion effectiveness. We are also interested in the flow regime identification. RTA definitely going to help us with more informed decision for future well placement and stimulation design. Despite the cumulative production could be a really great measure, RTA doesn't just tell us the well, how the well performed. It can show us how much it could be better performed. So this was the message that was communicated to engineer, and we will be happy to hear that. So with that message, I hope I got your attention to highlight the importance of why we are doing this course today. So the most damaging phrase in the language, I truly believe this quote by these pioneers. We always done it this way, so we're gonna do this again. Do it this way, maybe not the correct approach. So what I want to do right now, I'm gonna give you access to the software, so to see. During the course, when I'm presenting the course, you may be curious, okay, where this modules is sitting in the software. So you will be curious to just get familiar with the interface of the software. So let's go ahead and log in. So for the agenda of this course, I'm going to help with you log in and get access to the software. We're going to focus primarily on the RTA, mostly two methods that's implemented in Whitson. One is classical RTA, and the other one is a numerical RTA. I'm going to compare and contrast these two methods, and then we're going to have some exercises that fundamentally based on the concept and the theory that we will cover during the next little while. And what I want you to please go to courses.whitson.com, and I share my screen here. If you go there to courses.whitson.com, type in there, you should be able to see RTA course 2025 on the very top of your screen. If there are some issue for whatever reason you guys cannot see that, please reach out to the chat box and let us know. Hopefully everybody can see that. And if you go there,
can you show the team just the password? Just repeat that.
Yes. So once you are in this link, and then please log in with the email that you register for the course, and not your company email, but the email that you register, and put in this password, lowercases, uppercase, and 2025 is the password. And once you should be able to see this. And what I want you to do, please, underneath the project name, put in your name. I'm gonna put my name initials here, whatever name which is unique from your other participant, and click on save. So again, underneath project, I just generated Hamid B, which is the name of the project that I generated. And I want you to please go ahead and add that project underneath this and put your name for the name of the project. And we're gonna import some values under this project. I'm assuming everybody has created that, right? And in the project, if you go to please mass upload on the top right, in the mass upload, if you click on that one, this window will pops up.
I'm sorry. Could you please repeat the part where you created the project?
The project, okay. So in if you go to courses.whitson.com, and you should be able to see this RTA course 2025. Click on that one. Go there.
I see
project.
The project.
Yeah.
Okay.
Underneath the project, click on mass upload. In the very far right, there's examples. Click on the examples, and you should be able to see this interface. There's a RTA certificate vault. RTA certificate vaults. If you click upload, take a couple of seconds to upload these vaults, and then once uploaded, close this window, and now we should end up with 3 vaults. These are the vaults from SPE repository. So we're gonna whatever learn throughout the course, we're gonna use this data set for our analysis. So I'm assuming everybody follow me up to this step.
Sorry, when you clicked on your project, right, where it was writing private, when you click, mine is not
mass upload.
No, mine is not opening after that. Like when you click on your project name.
I'll fix it for you, Gurban. Just
okay.
I'll let Hamid continue there. I'll write you in the chat.
So far we have imported 3 values, and hopefully most of you guys were able to import these 3 values. I'm gonna go ahead with the rest of these slide deck for the time being. And okay, the workflow generally, once people talk about doing RT on the values, the general workflow is always start with the PVT and fluid properties. So we're gonna have a good idea about the PVT. The great thing about Whitson Plus is you need a minimum amount of information to generate the PVT information for your analysis. So I'm going to show you how dealing with one simple case, which is dry gas, and one more complicated case, which is oil well. And I'm going to show you how you can set up initialize your PVT. Second part is the bottom hole pressure calculation. There's a one dedicated course, and I highly urge you, if you are not familiar with how to do the bottom hole pressure calculation in Whitson, take those course. A lot of great stuff there. And then we do multi-phase FMB. This multi-phase FMB techniques give you how much of the rock you have so far contacted. So that's another technique. We are not covering this in this session. What we're going to cover most of these slides is analytical and numerical RTA. And lastly, depending on how much we are progressing throughout the slides, we also cover some simulation and forecast numerical simulation. So this is going to be the focus. So I truly believe that we need to get down to the fundamentals, and the level of everything after that you're gonna will rise. So I'm gonna spend a couple of slides on the fundamentals of RTA. The RTA, I guess you agree with me with the couple of first slide, how I presented the examples that present the urgency of using RTA, which is basically at the end of the day, the science of combining rate and pressure. And what we're gonna get out of that is we're gonna do the data interpretation to come up with some reservoir and completion parameters. We're gonna have idea about the matrix permeability, fracture half-length, if we have any scheme that's choking the well, and finally how much fluid in place we have contacted. And once we got this information, we have great tools in terms of modeling to plug in this number from our interpretation into our model to go ahead and do our primary job as a reservoir engineer, which is forecast. How much is well going to forecast in the next while? We're going to optimize our completion. We definitely have some control on designing the completion, so we have certain amount of XF, don't have much of a scheme. So they're going to help us this interpretation to optimize our completion. And we're going to benchmark performance. If two completion vendors complete their well differently and you're going to compare them against each other, the only way that you can do that is to consult the metrics, completion metrics, which comes from interpretation. And finally, and last but not the least, it can also support a strategic decision. Do I need to refract the well? Do I need to pull my wells in a closer spacing? How many fractures do I need to complete my wellbore with to produce economically after 1 year of production? So this is the cloud word. So a lot of this word, I'm gonna just pause here for a couple of seconds. So you'll review some of these terms here: RTA, BHP, SRV, the skin factor, productivity index, fracture conductivity. You might have heard of some of these words in the past, but this is the language that we're going to speak about. And therefore, we definitely need to be on the same page when we are talking about fracture half-length, what's fracture half-length, or what's the drainage area or numerical RTA. So this is a schematic of a horizontal wellbore that's completed with multiple fractures, and we're going to take advantages of a unit of symmetry. In this case, each of these fractures are identical in the sense that the way that we're going to treat them. We can take a quarter of these fractures as our element of symmetry. And we're going to define a linear flow parameter. Linear flow parameter is defined as surface area times a square root of permeability. What is this permeability? Is the permeability of matrix that's sitting in between each of these individual fractures. It's not the fracture permeability, it's the matrix permeability. What is the area? Area is simply 2xf. XF is half length of the fracture, so we'll multiply by 2 to include entire length of the fracture, times NF, number of fractures that we put in the reservoir, times H, which is the thickness of the reservoir, or more importantly, thickness of the fracture, times the square root of matrix permeability, multiplied by 2, because we are producing from both sides of the fracture, right? So LFP. The drainage area is simply the drainage area is defined 2xf times the length of the wellbore. So it's also important to communicate this with our completion. So if my drainage area for this well is this much, it gives me a very good idea where to put the next well. And finally, original fluid in place. It could be original oil or original gas in place. So that's also another metric that we need to be familiar with. Is defined as the carbon pore volume divided BTI. BTI is total formation volume factor. For oil reservoir, it is oil BO For gas reservoir, it is BG. And if you are in the two-phase, it accounts for the two-phase initial fluid in place as well. The way it is defined, simply it's volumetric plus some petrophysical properties, which gives us an idea of how much volume we have contacted. So this is the volume of the reservoir that we have contacted. And pore volume, we can communicate this with you both in the software or also in the slide deck through original oil in place, original gas in place, original water in place. For instance, if you are dealing with a gas reservoir, condensate reservoir, not only you report the original oil in place, original gas in place, but also you report the original oil in place, which is condensate in solution. All of these are interchangeably used. So they are very simply correlatable with each other through formation volume factor, solution gas in oil, and solution oil in gas, and some initial petrophysical property. Another important parameter is once we completed a segment of our reservoir, section of our reservoir through multi-frac horizontal wells, we're going to contact some fluid in place. We're going to produce from this region. This region could be a little bit different from what being petrophysically mapped through our geologists. And usually the geologists have the porosity map, thickness map, saturation map. They come up with a volumetric calculation of the original fluid in place, which most of the case, 90% of the case, 90% of time of the case is different from what we get from RTA. RTA always did with contacted pore volume. There could be some shale layers, barriers that has not been able, the geologists would not be able to identify on their map. Therefore, there's a disconnect, hydraulically disconnect from this segment of the reservoir to other part of the reservoir. So they are not in a full hydraulically communication. Therefore, RTA during the production life of the well would not be able to see those not very well contacted region. So therefore, we report a volumetric that could be different from the petrophysically mapped. So far, we are familiar with the linear flow parameter, original oil in place. Linear flow parameter defined at this point. This is OIP. Why they are important? They define the productivity index of the well during early time, usually correlatable with 1 year of QM, and during late time, which is well level produced during boundary dominated flow. So this, we're going to talk about infinite acting. It's a flow regime. And we're going to talk about productivity index during this time. And during boundary dominated flow, we're going to talk about original oil in place. So these two, you can imagine these are productivity index of the well during early time and late time. So these are two important metrics for the well that we need to, at the end of the day, be able to report them. And depending if they are high, low, and we're going to have 4 different combination of these two. So this is a great basically tool. If you are dealing with hundreds of wells, I highly urge you to just generate some map like this. And once you generate the map, put some threshold for the A square root of K and all original fluid in place. And then you come up with some wells populating in this quarter, some wells here, some wells here. But what would be the true meaning of this, right? If I'm sitting in this quarter where my well is taking advantage of high linear flow parameter and high fluid in place, this is going to be my sweet spot. This is going to be next phase of development. I'm going to put my next well in this area of the well. If my linear flow parameter is high, but my fluid in place, basically the juice of the reservoir is low, indicating that maybe I put the valve very closely to each other. So I need to go ahead with a wider well spacing. On the other hand, if my linear flow parameter is low and fluid in place is still high, through analysis of my data, I realize this is the case. Therefore, I have to reconsider completion optimization. Maybe refract these wells. And in this case, I wish none of your wells shows up here. Maybe you postpone your further development in this area unless otherwise some other information you receive, and you're going to include those in your interpretation. So multi-frac horizontal wells are, despite the fact that the completion, we call it unconventional reservoir in the sense that we complete them not conventionally, like a vertical well and completed only the vertical section of them. But if you just rotate them, and you can see there are a lot of similarity between the two. So but there could be a lot of differences as well. The main flow regime that we see here is the radial flow. The main flow regime that see here is the linear flow regime. The life of the ball going to be mostly in the transient. This was usually completed in the millidarcy type reservoir arc, going to be in transient flow for a couple of months. The productivity index during transient is dominated by KH, but the productivity is AS square root of K. So for RTA, any RTA study that we're going to do, we're going to focus on 4 different buckets. And they start with the more easier one, usually just plotting the data and getting a sense of the data, how the data is telling their story. They are telling to us, and then walking through more advanced tool. The first steps that we're going to do diagnostic. By diagnostics, it means what flow regime we are sitting in. Is it transient? Is it boundary dominated? And just visually looking at the data, first of all, plotting the data in such a way, maybe in the Cartesian plot or log-log plot, and looking for the changes of the slope that's happening, looking for the signals that the data is telling us. If there's changes in those signals, it's telling me that we are changing from one flow regime to another flow regime. It's very easy step. It's mostly visual and it's qualitative. The second one, you're going to compare relative well performance. So for a well producing from the same region, I can safely imagine my initial pressure is the same, the PVT is the same, the rock quality is the same. The only thing that could be different is the completion, right? How much access we have created in terms of the surface area, how much fluid in place we have contacted. So that's the relative well performance. This could also be at the same time visual, but at the same time we could put some numbers towards that. The third step, a little bit more complicated, is once we just focus of the course, which is the quantifying AS square root of K as well as the contacted fluid in place. So these are where we started to interpret our data, looking for the signature again in the data in some of the plots that we call them a specialized plot. Some of them are Cartesian, some of them are log-log, and we try to interpret the data, portion of the data that behave similar in terms of they staying on the same line, and we're going to interpret them and put some number. And at the end of the day, what really matters is to resolve all the physical parameters. This is the stage when the well experience both transient flow and boundary dominated flow. The well should be must be in the boundary dominated flow. We should have also some external information about how the completion has been conducted, right? How many fractures have we put in place? Once we have included those external information, then we would be able to decouple the element of AS square root of K and fluid in place. And that would be the interesting part of the story, where we're going to rely on this information to proceed with forecast, with completion design optimization, with well spacing optimization, field development. So we're going to start from easy to more advanced. Flow regime 101. So we define 2 flow regime mainly, is the infinite acting, and the other one is boundary dominated. Infinite acting means that each of the fracture hasn't filled any boundary. The boundary could be a physical boundary or could be no flow boundary simply because the pressure gradient is 0. We're going to talk to this flow regime in the next couple of slides. On the contrast, we have a boundary dominated flow, where the boundary dominated flow means that all the boundaries could be fracture boundary, fracture to fracture boundary, well to well boundary, or a physical boundary, like there's a shale layer that prevent the fracture height to basically expand beyond that region because of the stress is different in those regions. Those are called the boundary of the reservoir. So once we touch all of those boundary and the pressure has started to deplete on those boundary, all of the boundary, we call it boundary dominated flow. Everything in between is called transitional flow. So let's see some schematic definitely help us to redefine these infinite acting and boundary dominated better. This is one-dimensional model. This is from a reservoir numerical simulation model. This is the horizontal wellbore. The vertical fracture goes in the middle of this region. And you can see when we put this fracture on production, the pressure starts to propagate sideways onto both sides of the fracture. And there's only one boundary in this case here. And so this is boundary. How about in terms of flow regime? There's 2 flow regime. Early time, we call it infinite acting or transient. Late time, when we started to feel the pressure to drop at the boundary of the reservoir, we call it boundary dominated. Next, if we stack a couple of these fractures in the multi-frac horizontal wall, which we're going to be dealing today, going to be identical, similar story because this is our element of symmetry, right? Still, we have one-dimensional model, and we're going to in between there's a no-flow boundary that's simply created because there's a pressure gradient equal to 0. We could have more complex cases. In this case, with our fracture only extended halfway throughout the reservoir. So there's a region beyond the tip of fracture is also contributing. So it's called two boundaries. One boundary is this boundary, the other boundary is on the top. It's a two-dimensional model. In terms of the flow regime, we're going to start with the infinite acting, which is the early part when the pressure only propagate around the fracture. Then it's going to be transitional flow, where not all the boundaries has been feeling the pressure depletion, especially beyond the tip of the fractures. And thirdly, when the pressure propagate all the region, we call boundary dominated flow. So it could be sometimes very complex depending on the completion. For instance, here could be many different combination of infinite acting goes right in the boundary dominated flow. For instance, in this case, where there are fracture or spaced very closely, there's going to be a period of transient flow, then going to be boundary dominated flow. If the fracture are spaced more sparsely, more widely, it's going to be infinite acting for a quite long period of time before it's reaching to the boundary dominated flow. Or it could be infinite acting going to transitional flow when there's some flow from beyond tip of fracture, right? And it could be the case where we only have 2 wells per section or 3 wells per section. It could be these 2 wells, these wells in this rectangle can easily demonstrate different flow regime from infinite acting to transitional flow to boundary dominated flow. So this covers the first bucket of RTA. I'm not checking the chat box. By the way, if there's any question, I'm expecting Mo and Anna will inform me, please. So far, so good. Is there any question? Everything is clear. So could be signals that everything is clear or nobody is listening to me. Hopefully I get some like button here. Thank you guys. All good. Let's proceed.
I'm sorry.
And go ahead.
If for me, maybe 1 minute, could you please explain how we instantly change from TF to BDF on the
TF to BDF? That's a great
the
question.
second to the last.
The second of the last. Okay, TF to BDF, right? So imagine we aggressively complete a well bore, like this case, in this scenario here. So the transitional, the infinite acting period could be very short-lived, right? Because this fracture start to interfere maybe first month, first couple of days, right? Because we aggressively put this fracture closely to each other. Then if we're gonna go from a very short-lived infinite acting period to transient period beyond the tip of fracture to boundary dominated flow. Have I answered your question, sir?
Perfect.
I hope so. Okay, thank you. Let's proceed.
I also have a question.
Please.
I just wanted to ask you that what is the like? Can you show me the difference between the initial acting and the TF one in the previous
Initial
slide?
acting, infinite acting, you mean? I
Yeah,
guess, right?
sorry, yeah.
Okay, say that again, please.
What is the difference between the infinite acting and the transitional flow here?
Transition. Okay, so with the infinite acting, none of the boundaries has been met yet, right? So during infinite acting, you see, this is the snapshot of infinite acting. So the pressure start to propagate in the reservoir, but hasn't touched any boundary yet. The boundaries, if there's a gauge sitting here and measuring the pressure, the gauge is not measuring any pressure drop.
Okay.
Because, yeah, that's what we mean by infinite acting. It behaves as it acts as infinite reservoir. It hasn't seen the boundary yet. That's the meaning of infinite acting. We're gonna
Okay,
proceed.
Is it not the same with the transitional one?
Oh, transitional, the difference between infinite and transitional is in the transitional, it had already seen some of these boundary, but hasn't seen these boundaries. That means transitional. So we are transitioning from infinite acting to boundary dominated. It's neither nor transitional. So transitional means if you have 5 boundaries, I have touched 3 of them, but not 2 of them.
Okay.
Yeah.
Okay, cool. Thank you.
Of course. Two focus of this talk is two different RTA methods, classical RTA, numerical RTA. I'm going to spend quite a bit of time, maybe 20 more minutes on this one before we go for a break. If you learn classical RTA, numerical RTA, promise, it's going to be much easier. They're going to digest it like in 10 minutes. So just stay focused. We are still fresh in the course. So I'm going to walk you through classical RTA. What does it mean? And for our assumption to develop those models, we need to make some assumption. Always start with the assumption. It's always important for us to also review the assumption and revisit the assumption after we've done the analysis. So please pay attention to these assumptions. And there could be source cause of some of the confusion. We came across a lot of people asking questions, why this is so in my mini-Darcy permeability reservoir, despite the fact that the fundamental assumption got violated. So this is multi-frac horizontal wall completed with multi-fractures. As I said, is very well suited for element of symmetry. So if I take this rectangular and enlarge it here, a couple of fractures here, and they start to produce from these fractures, we're going to develop a no-flow boundary in between. So that could be a representative model that I'm going to develop the equation based on. So the other assumption, single phase flow with constant PVT. The only fluid that will pass this first assumption is water. We are producing from oil and gas reservoir. It's changing PVT drastically, especially for the gas reservoir. Other assumption, constant rate production. Barely produce constant rate production. Maybe during the first couple of months, we constantly rate restricted wells or choke backed wells. We produce at constant rate, and the well is always infinite acting. So there are these three main assumptions here I'm going to talk to you about and how we can alleviate some of these assumptions later. What would be the technique for accounting for these assumptions. So I listed these assumptions here. If you work with this element of symmetry that I presented here, we're going to end up this partial deflection. This is going to be a little bit equation loaded, but it's really simple. So when we impose this constant rate as a boundary condition for this problem, I'm going to end up this equation. And this equation, let's review some of these parameters that goes into this equation. Some pressure data, initial pressure, bottom hole pressure, Q, rate, surface, on the surface. We collect this information on a daily basis, right? These are readily available data. Next, there are some PVT data, formation volume factor, viscosity, porosity. Porosity is the reservoir properties, petrophysical property, and compressibility factor, and some other dimensions of the reservoir, right? We're going to call these MCR. CR represent constant rate, and M is simply because the slope. At the end of the day, we're going to plot this left side of the equation with respect to the right side of the equation. So this is Y, X, the slope. Linear flow parameter, the ingredient to make this linear flow parameter elements are here, but these elements also appear nicely here as well. So the slope, linear flow parameter are somehow correlated. We're going to simplify this, put in MCR. This is going to be my equation. We're going to define two terms, rate normalized pressure, pressure normalized rate. Very simple definition is based on the production data and bottom hole pressure. And this is the inverse of this one. It is called rate normalized pressure. Rate normalized is basically pressure normalized by rate, why they call it rate normalized pressure. It's called pressure normalized rate. Just for the simplification, but also because in all of our interpretation, this trunk of parameters shows up. That's why we need to know them by heart. And what this equation is telling me, if I plot my rate normalized pressure, delta P over Q, versus a square root of time on the Cartesian plot, I'm going to get the slope, I'm going to get a straight line. The slope of this straight line, MCR, this is a slope of a straight line, also inherits some linear flow parameter, combination of linear flow parameters. So don't worry about none of these. The machine is going to take care of the math. We're going to do the interpretation of the data, right? So I'm going to repeat it one more time. This is pressure difference divided by Q versus the square root of time, slope of the line, linear flow parameter. Somehow, a lot of these parameters, including the PVT, because they are calculated at initial reservoir pressure, are constant. So I can combine them in a constant value and include linear flow parameter, which is NF, XF, H, K, which also shows up here, into this equation and present it in this form. So my linear flow parameter is inversely proportional to the slope of the line. So question for you, if I have three wells in my basin and plot them delta P over Q, like what we should plot based on this equation, and they presented three different slopes, which one of these wells is more productive during infinite acting period? Because remember, this is infinite acting, one of the main assumptions here, right? Based on this equation, I'm pretty sure you guessed it right. It's a bigger LFE, big LFE, a smaller LFE, simply by comparing the slope of the line. So we can use this technique relatively, basically compare the completion of the productivity index of the wellbore with respect to each other. Another main assumption was constant PVT, right? is only water that qualify this parameter here. For well, with the oil well, for above saturation pressure, it's also a very fair assumption. So we can safely use this equation for undersaturated oil reservoir. But for the gas reservoir, it's going to be totally different story, right? The viscosity and compressibility of gas reservoir will change drastically with pressure. One simplest way to accommodate those changes of the pressure is through defining, instead of pressure, in the world of gas, we always define pseudo pressure. But what is pseudo pressure? So this, for the gas wells, again, the same form of the equation is preserved, indicating that we plot this part of the equation with respect to a square root of time. We're going to have the same slope. We have similar to the oil well, but here, again, there are going to component of linear flow parameter in both of them shows up. Porosity shows up again. Viscosity and compressibility and the rest of them, because we have an equation that define the formation volume factor for gas. So this is show up like this, the temperature of the reservoir, and also the viscosity show up on the denominator. But these two equations is basically, they are the same. So for the gas reservoir, we define pseudo pressure. This is the way we define it. And why we define it? Simply because it somehow linearized gas equation. By linearization means that it accounts for the changes of the PVT property. Let's go ahead. We also we have made the assumption that this is for constant rate. The equation is valid for constant rate. In 99% of the cases, we're dealing with the variable pressure, variable rate. And therefore, we need to somehow accommodate those changes. We define a kind of time function. We call it superposition time function. And the superposition time function in this case that most of the industry are used for the analysis is called material balance time function. Originally, so the intent of this time function is to convert variable rate into constant rate solution. And it's work best if we are in the boundary dominated flow. But can we use it if we are in the infinite acting? Because another assumption that was that we are in the infinite acting. The answer is yes, but it comes with some error. Could be 20%. But if you are doing something wrong consistently across analysis of the wells for our pad, we should be good when it comes to the comparison. So why we rely heavily on this material balance? Simply because the mathematics is so simple. It's defined as cumulative production divided by Q. So you know the daily rate, you know the cumulative, you can simply construct this equation, material balance time, and it can be easily calculated this way. So far, we have covered the constant rate, infinite acting, constant PWF, PVT, single phase flow. We haven't covered that yet. We're going to talk about that, what issue can bring to us. And 1D was the element of symmetry with no flow from beyond tip of fracture. So with the infinite acting, let's tackle this issue as well. So this is comes back to the flow regime that we just talked about. It takes a little bit of time for the pressure that we start to propagate from the fracture far into depth of the reservoir to reach to the boundary of the reservoir. So if this boundary, you can imagine it was a long boundaries, we were expecting this line to be a straight line. But by the time we hit the boundary of the reservoir, right, we start to show some upward curvature. And this upward curvature, because we are transitioning from one flow regime, which is infinite acting, to boundary dominated. And remember, Q is sitting in the denominator, indicating that by the time we reach to the boundary, now we have a limited reserve to produce from. So for the same amount of delta P, we're going to produce less Q rate. And because the rate is sitting in the denominator, it starts to curve upward. So if I have different wells that start to depart from this straight line, I'm going to ask you a question. Which one of these wells has less original fluid in place? Simply by looking at these plots, the time that they start to depart from the straight line. And I'm pretty sure you answered that correctly. The time that depart reflect the how much OIP. And it clearly, so you can imagine if I extend this fracture a little bit more, it takes a longer time for the pressure to reach to the boundary, therefore it takes longer time also to depart from a straight line. So we're going to take the time to end of linear flow by the time to end of linear flow, time to end of the departure as, okay, this region of, so if I'm investigating this wall, you're going to be my infinite acting period, you're going to be my boundary dominated value. For this wall, you're going to stay on the straight line for a longer period of time before a departure. So it's going to be my transient flow. It's going to be my boundary dominated. So based on that one, we're going to define a time, which is time to end of linear flow. And time to end of linear flow is a really great information that we need to have in order to estimate the permeability of the reservoir. So this is our characteristic plot, or a square root of time plot, a specialized plot, different name associated with that. And with the we use also a definition of distance of investigation. How long distance of investigation means how long would it take for pressure to propagate and travel certain distance. So you see, this is the distance to travel. There are some constant into that. Similar to rest of equation, there are some PVT and petrophysical properties, but the permeability of the reservoir and time will show up on the denominator. For the time that it takes for pressure to travel from the fracture phase to the boundary, what would be the distance? The distance would be simply the lateral length of the wellbore divided by number of fractures, which is this element of symmetry. And since the pressure propagating both ways, I need to divide it by 2. So this is the distance that the pressure need to propagate from the fracture phase to get to the boundary. This is basically YE, we call it by YE, which is lateral length divided by NF. This is my element of symmetry divided by 2. This is half of the element of the symmetry. So I know the lateral length of the wellbore. I have some information about the number of fracture. I'm going to calculate YE, plug it back here. The end of linear flow come from this specialized plot, plug it there. I know the PVT properties, therefore I can solve for K, and permeability is known. Once the permeability is calculated, I'm going to go to my slope. This is the definition of the slope that we had, both for gas and for oil. And the permeability is known, the slope is known, all the PVT property is known, porosity is known. Therefore, I can calculate for HF and XF. And once I know the combination of these two, I can solve for my original fluid in place. Here are elements that goes in the original fluid in place. XF times H, this is XF times H, and the rest of that are PVT properties and petrophysical properties. Therefore, I can calculate original fluid in place. This is how we use classical RTA to come up with linear flow parameter as well as the original fluid in place. Is there any question?
Could you cover the differences of different superposition times? I know you primarily focused on MBT earlier.
Absolutely.
But like choosing one is important depending, I guess, on the well, where the well is in its life cycle. Could you talk about how it could skew the outcomes of the insights and the analysis depending on the pick?
Absolutely. That's a great question. What would be the proper superposition time function that we need to use for our interpretation, including linear flow parameter, OIP, and flow regime identification? I don't have the definition of linear superposition time in my slide here, but what I can promise you, once we are going through the analysis of the well for one of the well, I can present you how different time superposition time function will treat the data and what's the caveat of using one against the other one. But for the time being, let's stick with me where we are right now. Use of material balance time function for your analysis is really good enough. I know this is the limitation of classical RTA. Once we are in the realm of numerical RTA, everything is going to be much more simplified. We're going to talk about time and space, no superposition. But as somebody who are doing the analysis for this multi-fracture horizontal flow, you definitely need to learn about the superposition time function. Do we have any other question? We're going to take two. Yeah.
Actually, yeah, one quick question. If you go back to the slide where you're asking us how to determine which well has the smaller or larger original oil in place.
Yes. Yeah.
So what if we want to compare wells with different lateral lengths?
That's a great question.
Yeah. Do we normalize the Abro-K parameter per foot, or what would you recommend we do?
Okay, that's a great question. This is for demonstration purposes, right? So if we deviate from a straight line at this point versus this point, this is not only the time component that goes into that, number of fractures goes into that as well. The permeability goes into that as well. The XF also goes into that as well. For OIP, so we take that T end of linear flow and plug it back. I will show you in the software how different components are related to each other. So picking picking the time to end of linear flow is this is not the full picture, but keeping everything consistent in terms of the number of fractures, in terms of the height of the fracture and the PVT. This could be relatively a good indication that for the well in the same path with the everything like the PVT is similar, this could be an indication of the time to end of linear flow indicates because it's directly, if you take a look at this equation, like the higher the time to end of linear flow, could be. So if your the lateral length of the well are the same, the number of fractures is the same, therefore YE is the same for the same PVT and porosity. If you double the time, if you're for one well, the time to end of linear flow is double the other well. This means that the permeability is half of the other well, right? So do we need to normalize them? Definitely we need to normalize them. But classical RTA as well as numerical RTA will if we do the interpretation of the data which are in the boundary dominated flow, which would be able to give you the original fluid in place as well. Okay. So let's go on. And so at the end of the day, we're going to be dealing with some plot like that, maybe 3 more minutes, and we are ready for a break. And so this is the plot that we're going to see. There are a couple of important parameters here. First of all, the slope, shallower slope, higher linear flow parameter. Time to end of linear flow is also important because we need to calculate original fluid in place was based on this information. And the third one I didn't get a chance to talk much about is the intercept on this one, which is also reflect kind of the skiing effect or the conductivity of the fracture, right? So usually for the skiing, we add additional term representing additional pressure drop. And this additional pressure drop is, so if we go through the intercept indicating B is 0, there are not additional pressure drop due to a skiing. But if you have some intercept indicating there's a skiing, if we have a higher intercept indicating there's a higher skiing. So a skiing by itself, that number doesn't have any meaning. What really matters to us is how much pressure drop it created. And it not only due to completion, there could be many other factors. We can have a discussion about these. Could be finite conductivity. It could be in the pressure. I'm going to show some of these effects once we are doing the analysis on the actual data. And if you wrongly input the initial reservoir pressure, how it's being interpreted as a skiing on the intercept. Could be damage due to finite conductivity. So because finite conductivity and wrong pressure are 2 different stories, but they manifest themselves with the same behavior on the y-intercept. So for us as interpreter, we should be able to decouple. Sometimes we have really hard time to decouple them. Sometimes we can decouple them through some of the tools that we have. Is usually derivatives, is some information about the fracture itself. It could be if it is the pressure dependent or proppant crushing. So all of these listed items on the bottom have the same impact on the behavior of the line, but if I interpret my data and come up with the intercept, now I might have some hard time say this is because finite conductivity, or could be due to proppant crushing. So to summarize, these are the 5 features from classical RTA, and at the end of the day, we're gonna this is the dashboard where we're gonna see once we are interpreting our results, and these are different parameters that goes. I will recover some of these while we are analyzing the data, and also with the derivative, I'll come back to that. So far we covered different buckets of RTA: diagnostic, relative well performance, AS, square root of K, OIP, and resolving parameters NF&H. Do we have any question? I see a raise hand. Please go ahead.
Yes, I have a question. This skin that you are getting from the RTA analysis is comparable with the one we are getting with the PTA?
It's a great question. It's in the realm of RTA coupling with the PTA. Usually PTA is much better in estimating what's going happening in the near wellbore region. RTA only demonstrated in the skiing effect, but PTA, because we are not producing from the reservoir, is usually everything is so quiet, so we are monitoring what's going on in the near wellbore region. But to answer your question, yes. If you have some build-up data, we're definitely going to value those to identify what's going on in the near wellbore region much more than what we do on the RTA side.
So basically, with the RTA analysis, we will have an idea that there is some kind of damage in the near wellbore, but the most accurate value is coming from the PTA. We can say something like this, right?
I can say that, yes, sir.
All right, thank you.
I guess all of us deserve 10 to 12 minutes break, if you agree all, and let's come back in 12 minutes. And if there is any question, I would be happy to take them. If not, let's take 12 minutes break. It's 10 a.m. Houston time, so maybe we come back here 10, 12.
Did you say you will take questions while
Of
we're on
course.
break? Very
Please.
good. I wanted to know, so the OFIP formula with the HXF and F
Yes.
parameters, this is for fractured horizontal wall. If I have a tight gas without fracture, I just know that the property is very, and I want to
Yes.
do an RTA on it.
Yes.
I can just take out this HXF and F, and I assume that the denominator is square root of K, and that will
So-
still be applicable and all analyses are still in place.
All analysis are still in place as long as you believe in that there are minimal contribution from beyond tip of fracture, right? So
Yeah, I'm
it's a
just I'm
few-
actually assuming that there's no fracture. Actually, that I have.
Oh, there's no fracture.
Maybe I
So-
have some high perm streaks here and there,
Oh,
but
okay.
nothing, not structured like you would have.
Okay, I see. In those cases, I would say no.
Okay.
So there are still some certain module in the software that you will be helpful to you, and the main one gonna be fluimetry balance. So because the fundamental flow regime that we are trying to solve, you see, I started with this partial differential equation, right? We are solving all the solutions based on this PDE, partial differential equation.
Yeah, but that should be also applicable to matrix situation.
So
or not.
if you don't have a fracture, so if your
Yes.
configuration is, I had a slide that specifically talk about the similarity between vertical well and multi-frac horizontal well, right? So the fundamental flow regime here is radial flow, but this one
Exactly.
is
So
linear flow.
we are assuming
So-
that these are perforations in the vertical well.
Yes, these are the perforation, but
Mhm.
it's just exaggerated a little bit to make my point and say,
Yeah,
so
yeah.
you got my point, right?
I do.
Yeah. All good.
All right. Okay.
Yeah. Okay.
See that.
All good. Let's see hands up, Brian. Shall we start? Couple of thumbs up, say yes or no, I guess. Daniel, do you have a question? Just want to confirm if you can hear me okay. Jessica, if you don't mind, if you can hear me okay.
Yep, all good.
Okay, wonderful. Okay, so hopefully everybody enjoyed their break here. And hopefully in the first part of the presentation, I was able to highlight the importance of ray transient analysis. This is going to be a simple intro to the science, the experience that you're going to gain while you're interpreting your real data, the behavior, and try to attribute some of these behavior to some physics that's not included in the development of this equation, right? You'll see how many items that I highlighted to be the main assumptions for development of these equations, and but there could be many more, right? We didn't tackle the fracture itself, because the fracture is a different media than the matrix. We are trying to do interpretation based on the matrix, but the fracture itself could be finite conductivity. We somehow are able to identify if the fracture is finite conductivity or not. But in most of the cases, for instance, if there's a pressure-dependent permeability, which a fracture is more prone to demonstrate those type of behavior, it's going to be a little more difficult. But it comes all with the experience. But hopefully, we are able to mention at least some of those complex behaviors, so you keep those in mind. And once you're interpreting your own well, your own data for your own well, which is the ultimate goal of these, using our software, and be able to interpret actually the physics that's going on there. So I'm going to highlight a couple of points here. That's in this course, we don't have much time to investigate these items, but we're going to assume that all the PVT properties, bottom hole pressure, initial pressure calculation, is correct, and we don't want to do some due diligence studies about it to just question them. So make sure the sources of the information for those are correct. And the second one, do the data validation, put it first. It's a very first critical step. 25%, 30% of your time should be dedicated to validating your data, because you're going to put your interpretation based on those data. Bottom hole pressure calculation goes in each of those calculations. The PVT properties goes in each of those calculations. Initial reservoir pressure, so it's going to impact your interpretation quite significantly. So make sure you do the data validation step first. The other important part in a conventional world, especially if you're very familiar with the PTA in a conventional wellbore dynamic, can screw up the data quite significantly. In the multi-frac horizontal well, it's not only the wellbore, but the fracture itself also play critical role, that we need to be able to understand those dynamics of the fracture as well as the wellbore. And at the end of the day, we're going to put a lot of emphasis interpretation on the matrix, characterizing the matrix permeability, etc., rather than the dynamic of the wellbore. And also we should be able to interpret the fracture itself. So and with that, make sure you integrate all the related information. If there's a frac job happening in a near well, if there's a parent versus child, those sort of challenging stuff, you should be able to do to integrate all the additional information that usually doesn't come into the software. So you're the one that in charge of making sure that you communicate with the production engineer, with the completion guys, and with the completion of other wells in the region, how they may impact the interpretation of the well. So those are a couple of important points. I really find it very valuable to communicate it with you guys in that front. And before going to the numerical RTA, I'm going to spend a couple of time, maybe 15 minutes, going to the software itself. So we see what we have so far presented, where you can find them, right? And especially some of the questions that I didn't get a chance to address on the different time function, how would it impact our interpretation? And so how many of them are the limitation of this classical RTA, and how many of them could be addressed once we are dealing with the numerical RTA, which is more sophisticated and deal this data rather than analytical. The point that I might miss is analytical versus numerical. Analytical are physics-based, of course. We solve the physics of the equations based on the equation that we are trying to solve, because they are analytical, are very, very, very fast to deal with, right? And the way that we demonstrate them in terms of the slope and time to end of linear flow is also very a strength of them, as well as the how we can show the data, the fact that they show themselves on the straight line, and we can do the analysis based on the straight line. These are also very interesting part of the analytical. While numerical is a different word, we grade everything differently, and I have a very interesting statement that compare the numerical versus analytical. And with that, I want you to please go to the software, and we're going to take a look at the one of the walls. So if everybody please go to the software, and we have so far uploaded 3 walls, as I said. These are the data repository that SP put together. Great work. It's actual data. So, and we assume that the PVT, as I mentioned in the first place, the PVT, etc., are trustworthy. So we don't spend much time in analyzing the bottom hole pressures. Let's take a look at this well at the bottom, 37 Pheasant well. Click on that well again in the well location. The very bottom well, Pheasant. Click on that. And before we go through the analysis, I want to make sure you get familiar with the software a little bit. So this is a web-based, so depending on the browser that you're using, you can easily adjust the screen size, the zoom of the browser. If you go on this 3 dot on the top right here, and you can see there's a zoom that you can settle on 80, 70. I'm very comfortable with 80, but If you want to adjust it based on your favorite, please go ahead and adjust it. And in the first page underneath, so they start with the field. So it started with the RTA course in the project. I'm assuming everybody created their own project. This is my project, and there are 3 walls in my project. I can search for the walls, and in this case, if I type in 37, so my well going to show up here. There are a lot of capabilities here as well. We can add well. There are a lot of attribute functionality here. Once you interpret your result, your data, you will be able to see all of the interpretation, even different type of interpretation underneath the result. You can edit all of them, bulk edit them, bulk export them, make group out of them. So there are a lot of functionality. Make sure you just get familiar with those functionality. Is definitely will be really helpful if you're dealing with the handful of wells. So more than 20 wells, you definitely need to get back to each to this option here, so you can compare and contrast the result and the result of interpretation. So in the wall, if I click on the wall, it's get me to the scenario tab. So you can create as many scenario as you wish. So this is the only scenario that I have so far. Maybe you're gonna adjust some of the parameter, but you don't want to change the parameter in the main scenario. You can simply create one scenario underneath this tab, add a new scenario, adjust your parameter here. And I get back to this page later as well. So this is the PVT where we input our PVT information. So quickly click on that. And if you click on the edit reservoir fluid composition, so underneath PVT reservoir fluid composition, if you click on the edit button, I'm going to give you some information. This is a dry gas well, and we're going to take a look at the production data as well. But now stick with me. So because this is a dry gas reservoir, for the PVT initialization, from this drop-down list, underneath method, there's a drop-down list. Click on that and select dry wet gas. So dry wet gas, select on that one. And so my method of initialization is dry wet gas. Reservoir temperature, 130. Initial reservoir pressure, 4550. This comes from the information that we populated in the scenario section. So these are the input parameter. We're going to leave them the same. Underneath gas-specific gravity, type in 0.6. So type in 0.6 for the gas-specific gravity. This indicates it's mostly 95% methane, right? And if you have some impurity, in this case, we don't have an impurity, but you can put them in. And once your screen look like this, click on save. Click on save, and it takes a second to generate this PVT. In terms of, because this is a dry gas, it's a little bit boring, so there's no phase envelope generated. And we didn't expect the phase envelope to get generated, right? It's simply because it's a dry gas. Underneath PV, if you are interested to see what's the viscosity, compressibility, the rest of parameters, click on the PVT tab. Underneath PVT tab, you can see gas formation volume factor, right? The GOR for the dry gas is 0. Gas viscosity is this one, and also some information about the, if there's a dew point. In this case, there is no, this is dry gas, there's no dew point, and some PVT properties at initial reservoir pressure. Now you have the capability to export all of this information to third-party software, or for your own information, you can export it to simply Excel. All of them are going to be tabulated there. Simply here, you can also click on some of this table, and you have this information here. So this is a PVT. Let's move on to the production data. This is on production data. So all of these plots that we have implemented in different segments, they are all interactive, right? I see there's a composition. What about composition? Okay, let's get back to the PVT. If we put in 6.6 as the specific gravity, I say 95%. Honestly, I didn't know that. I'm going to check it underneath this eye icon. So if you click on that one, the software will automatically generate a composition, 92%, right? So this is a representative composition. But if you have PVT report from soft vendors, you can go ahead and plug them in. Okay? So this is the composition part as well. If you go to the production data tab, and then it's the production data tab. So there are some functionality of the plots in Whitson that it's really make your life easy if you want to just investigate some portion of the data. I'm going to show you quickly in a couple of minutes how does it work. So on the axis, if you want to adjust the axis, you go here and you can simply adjust the axis when the double head arrow shows up, right? If you are in the middle, in the title section, it disappears. So you need to a little bit go above the title. So you start to see that, right? Similarly on the bottom and also on the side as well. If you go to the corner, all the way to 4 corners, you see this double-headed arrow diagonally show up. You can grab it and you can shrink it and you can expand it as easy as that. If you create a rectangular, just the click and drag, you're gonna create a zoom shape and the data show up. You can click as many times as you wish. Okay. Anywhere on the plot, if you double click, you're gonna zoom out to reset the axis again. If you are interested to adjust the axes to certain values, for instance, between 5 days and 9 days, you can click on the corners and put in those numbers. So it's just your axis is gonna reset to those. Right? There are some functionality here as well. Reset zoom. Click on the reset zoom. The tabular format of the data, you can quickly view them, copy them, and you can put some comments on different segment of that. This date, what happened? This date, what happened? And you can put in the well-bore schematic as well. So what happened during this? So a little bit about selection of the plots. So if you double click on the legends on one of these stream, for instance, in this case, gas only show up. You're gonna put in the pressure. They're gonna see, okay, what happened at this point? You're gonna zoom in here, and the zoom in you can drag and make a square, or you can horizontally move your mouse or vertically to only zoom on the x-axis. So if you do so, I'm gonna see what really happened here, right? I'm gonna put in the pressure overlay to this plot and see, yeah, the pressure suddenly dropped, therefore the range goes up. And you can sequentially add different plot or remove them if there's any gas lift or if there's any, how much is the water production, right? So resetting the zoom, there are some of the functionality. This applies to all the plots in all the segment of the software. You're gonna have this same functionality. So just get familiar and feel comfortable sometimes. And we can also use cumulative. You can date versus time. So these are some of the functionality, log, use cumulative, etc., etc. Okay. So this is about the production data. As a decline curve analysis and bottom hole pressure calculation, we assume the bottom hole pressure calculation is realistic, and we don't want to do some study if they look realistic. So if there are gauge data or if they are calculated from casing, tubing pressure, etc. And fluid material balance, I talked to that as well. These are the 2 segments that we spend in the morning. We cover the analytical RTA, or so the numerical RTA. As long as you know the analytical RTA, if you feel comfortable with that, the analytical RTA, the numerical RTA should be very, very much easier than the analytical RTA. So these are the 2 modules that we're gonna spend most of the time here. Numerical model is advanced form of numerical RTA, and nodal analysis mostly for the production data. There are some multi-well modules as well for the typal auto forecast. A very great module in the software is a comparison plot. So with a comparison plot, you remember I mentioned about bucketing your wells into different quadrants, and with respect to linear flow parameter and original fluid in place, all of those plots can be very easily be implemented in a comparison plot. In a comparison plot, we are getting to the capability of the Spotfire. There are a good chunk of works that you can do in the comparison plot. All of the parameters from your analysis, from production data, from numerical simulation, from all of these modules are accessible in a comparison plot. Just take a little bit of time, just familiarize yourself, at least take the certificate for the comparison plot. It's really will be really helpful, because at the end of the day, you're going to present these to the rest of the team, to the managers, and would be happy to go to the analytical RTA and say, this is my first scenario, second scenario. All of them can get populated in a comparison plot. If we get some time, I'm going to show you like at least how we generate some of the plots here. And these are something related to multi-well numerical simulation, gas lift optimization, group forecasting, and these are the well testing modules, and these are some PVT. So let's get back to the production data. So this is the production data we're going to analyze. In the scenario section, also a lot of information. This is also great if you can populate some of these information. For instance, if you're going to have the same the pad name, the same producing from the same reservoir, it would be really helpful to when it's come to the comparison plot for 100 wells that are producing from this reservoir, this is approximate EUR, or this is how much they cum after 12 months. So if you populate this information, those will be really helpful. So for this reservoir, initial reservoir pressure is this much, temperature is this much, and the reservoir height is this. And what I want you to do, please, for now, plug in matrix gamma equal to 2 and fracture gamma equal to 2. We're going to get to this in a little bit here. And once you update the information here, including the reservoir pressure, all this information in the reservoir properties, it's going to show up in all the modules that we have here. On the completion metrics, I see some of you guys might have question about the number of fracture. It's one of the not unknown parameter, but it's one of the uncertain parameters. Usually, the rule of thumb is to multiply the number of cluster per stage times the number of stage, and that gives you the total number of fracture, which is 90% of the time we are not creating all the fractures that we designed. It's usually comes with a completion efficiency, which is could vary between 70%, 80%, 90%. So it's your guts that's telling you, okay, how many of those fracture actually has been created in the reservoir. So that's something to keep in mind. But you can input those information. And there was a question related to normalization. Do we normalize with respect to lateral length? This is the lateral length, or the number of fractures. So this is a state, this is cluster, but the number of fractures is not simply, Whitson is not simply the multiplication of this. In this case, this is the input from SP repository. So this is not the simply multiplication of this. In this case, it's assumed that the number of fractures is the same. So with that, these are also some production metadata. And with that, I want to proceed with the analytical RTA, please. If everybody can go to the analytical RTA. And this is the interface that we're going to see in the first place. Once we are analyzing, this is a dry gas. This is a dry gas reservoir. And I'm going to put on a slide back again here real quick. We talked about this is the same data, but we're going to plot them in a different way. Why we do that? Simply to highlight a different feature. And one of the feature we're going to see investigate is flow regime identification. So by default, when we are in the module, there are different time functions: real time, material balance time, linear superposition time. I'm going to distinguish between material balance time and linear superposition. Industry standard, I see a lot of people are comfortable with using material balance time, despite the fact that this material balance time is developed for boundary dominated flow, but we still use it for the transient flow with a good accuracy. It's really with a good accuracy, and simply because it's very easy to understand. Linear superposition is a time function that it's developed for, first of all, as the name implies, it's a linear. It is for linear flow regime, and it is the time function for the transient period, not for the boundary dominated period. So this linear superposition time function is for transient period, works best in the transient period. Material balance works best for the boundary dominated flow. When it comes to determining linear flow parameter, right? Either of these should be okay to use the linear flow parameter. But if you have sudden changes of pressure and rates, I would rather linear superposition time function, because it take into account the sudden changes of the pressure and rate at the wellbore. But material balance time is a little bit less, is not as strong and effective at linear superposition. That's only true when there is a sudden change in the rate and pressure at the wellbore. So keep that in mind. So let's go ahead and click on auto feed. Once you click on auto feed, the software automatically find the linear portion of the plot and put the vertical line on the part of the data when it see there's a meaningful change from the deviation line. So it's really depend on who interpreting this data. So if I zoom in here, the same functionality of zoom here, right? You may argue, well, my data start to deviate at this point. My data start to deviate at this point. So it really depends on who is interpreting this data and how comfortable they are with interpreting this data, right? And since we are using the material balance time function, so with the material balance time function, if I click on zoom, and so if you're in this plot and you zoom in so closely, you can either adjust it and reset zoom. If you reset zoom, if for whatever reason your line disappeared, you don't see your line, you have to zoom in, and then what you can do, you can easily click on reset button here, and the data show up, and the line will show up. So what I'm gonna do, just to give you some idea about the material balance time, what I'm gonna do, I'm gonna go ahead and adjust this line on 20, a square root of time. To be perfect, I have to make it 400. So if I zoom in, it's on 20 mark. But because this is material balance, a square root of time, as I showed in the plot, therefore 20 by 20 is 400, right? But this 400 is a material balance time function. If your completion engineer asks you how long would it take for this well to start to go from infinite acting to transient to boundary dominated, you may say, oh, okay, it took 400 material balance. I would say, what is material balance time, right? Therefore, you need to translate this material balance into real time. And this dashboard on the right is telling you the story. So if I zoom in, this line and this line are correlated. So if I adjust this one, you see the line is also changing. So if I reset back, so if I set it at 10, you see how it is changing. Now I'm gonna go ahead and put it on 400, 420 on this square root of time. I'm gonna zoom in to see it takes 284 days in the real time to transition from linear flow to boundary dominated flow. Right. So on the bottom, we got to the flow regime identification. So there was a very good question by one of the audience here. What time function do we need to select for flow regime identification? The first choice, definitely put everything in real time, because material balance time function, imagine based on the definition of the material balance time function that I provided in a slide deck, this is, imagine for whatever reason, there are some operational issue, you wanted to close off the choke on the surface and the rate goes to very small value. What will happen to the material balance? The cumulative wouldn't change that much, but if the rate goes really low, the material balance time gonna be really high number, right? So that's the artifact of the way that the material balance time function is defined. So with that, you can see some of these small rate, this small rate could be way over here. The material balance time function shuffle the time data back and forth depending on how much rate they are. So the first thing first, I'm going to put it on the real time. I'm going to plot my data. I'm going to expand it. There are some functionality here. One of them is a slope of half a slope, indicating we are in the linear flow. Why half a slope indicate we are in the transient linear flow is getting back to the equation. We are plotting rate normalized pressure versus the square root of time. And we are in the log space. So if we took log from both sides of the equation, there's a square root of log of a square root of time is half of log of time. So this is log of time, and therefore if I put the half slope line, you see the data clearly showing you half a slope line, right? A good chunk of the data is half a slope. And the unit slope is basically when we are producing from the reservoir is a time type behavior. So the data clearly show you the unit slope line. So I'm confident qualitatively, I don't want to put any number here. Qualitatively, I'm going to say, yeah, this data shows some boundary dominated behavior. So let's collapse this plot, and I'm going to go ahead and now change my time function to material balance. And remember, we are not paying attention to linear flow parameter or OGIP for now. We are doing flow regime identification as a first bucket of rate transient analysis. So you clearly see once I'm toggling between real time and I'm gonna pay attention to this part of the data here, right? And if you select material balance time, you see how the data get biased towards the selection of material balance time. So what's telling me is say, oh, the data stay on the linear flow and the transient linear flow for a longer period of time, which is, we believe it could be wrong, right? And it's more pronounced when we switch to the linear superposition. So linear superposition time will biased your data towards being more transient linear flow, and see what will happen to the bottom left plot. Say when I select this one, all of the data is going to be get biased towards they are still in the transient flow, right? And see how the data will change on the, so all of these data are somehow correlated. So if I select my material balance time, I see the deviation happen at this point in time. If I select real time, let's see, well, the deviation may happen at this point in time. But if I select the linear superposition time, say, then therefore I have to put my line over here, right? It's give me huge OGIP. Remember, the location of the vertical line, I will get to that shortly, is telling you about the OGIP. So these are some of the limitation, not the limitation, is inherently, once we are developing these tools, they are already there. So we need to find some ways to deal with them. Something that I wanted to point out to you. So let's switch back everybody to this material balance time. And in the material balance time, I'm going to focus your attention. If I go to the production data, that's why I really highlight this to spend a good chunk of time focusing on your time on your data. There's a sudden change of the rate profile here. The rate jumped from almost 30,000 to 40,000. So it is 30% increase in the rate. I'm going to see how this data will show themselves on the analytical RTA. So if you go back to the analytical RTA, so I see clearly the rate is changing at this point here. So I can highlight it a little bit. See, this is a rate increase. And I'm gonna see. I'm assuming that you see this part of the data here shows clearly on a different slope, and it's just because we introduced a sudden disturbance at the wellbore. I'm gonna go ahead and select this one. There's a tool as you see sitting in the middle, and I'm gonna lasso filter. So I'm gonna filter some part of this data to see, because it's on a material balance time. I don't have any idea on the real time. So I'm going to select them and see it's clearly at the time when we see a sudden jump in the rate profile. You need to be comfortable with just doing the analysis, not only with one dashboard, but also multiples of them, right? How the pressure perform, how the rate perform, how does it look like on the log type curve, how does it look like on the specialized plot, the square root of time, right? So one more thing I'm gonna cover here. So before doing the analysis on this one, I gotta include the two options that we have here. As one is plot derivative, the other one is plot integral. Let's quickly take a look at the plot derivative. What derivative does basically is magnify the signals. By signals, what I mean by signals means that deviation from half a slope line. By the way, you can also remove this one or add a quarter. Quarter slope is related to finite conductivity fracture. So with a half a slope is the transient linear flow, a unit slope is the boundary dominated flow. So I'm gonna include the derivative of the data and see if my data are clean enough, the derivative gonna be clean enough. So you see a sudden change of the operational change at this point that we saw the rate increase shows the disturbance in the derivatives. But what's really interesting about this, instead of doing the analysis on my actual data, I'm going to do the analysis on my derivative data. And I'm going to move this half a slope line to derivative and see how nicely the derivative data will show themselves. So I also presented some stuff about the skin effect. I say there could be many combination of parameters that manifest themselves in the intercept on the square root of time plot, and derivative will be able to help us identify some of those. For instance, if there's a real skin due to some damage or some phase trapping, they will show themselves as an intercept, but the derivative, when we take the derivative of intercept going to be equal to 0, so they're going to demonstrate as the half a slope. But if we are dealing with a finite conductivity also will be demonstrated at the intercept on the y-axis. There's another line, quarter line, that we can put it in and say barely any of these data maybe initially shows the quarter slope and transition into half a slope, and then gonna move this one into boundary dominated flow, right? So these are some of the capability of the derivative. Limitation of the derivative, we need to work with a very clean data set to have a meaningful signature through the derivative. If there's some noise, then we're going to be in trouble. So let me show you quickly like wrong. So I'm going to remove the plot derivative and reset my plot and reset zoom. So this is then click auto feed. You don't need to do this, but I'm going to show you if I wrongly input a higher initial pressure, how would my data will tell us that about that initial pressure. So instead of 4450, I'm going to plug in 4950, right? And if I click OK, look at the data, right? This was the initial part of the data, and now I'm interpreting this. So there's clearly some intercept. I'm going to go to make my point. I'm going to make it a little bit more 55, and then see, this is just to see how the data will show the intercept if I put in wrong initial pressure. So for the initial source of initial reservoir pressure, some people rely on the flowback analysis, some people rely on the defeat analysis. So there could be different sources of initial reservoir pressure, but we need to be careful that if we plug in the wrong number, they're going to be intercept. And if I wrongly attribute this intercept to finite conductivity and advise my completion team that we need to put more propellant in the fractures to relieve those fracture conductivity, despite the fact that my initial reservoir pressure is wrong. So that's something that we need to identify if this intercept is coming from the actually wrong initial pressure or finite conductivity. By the way, this is only initial pressure. Whatever goes into y-axis is initial pressure minus PWF, right? So the same is valid for the PWF as well. So let's a little bit talk about this slope. So for this one, the contacted OIP is close to 40 BCF. And if I adjust this slope and make it shallower, I'm expecting my linear flow parameter. So this linear flow parameter is close to 500,000, right? Now I'm gonna make it shallower and see how does it change. If I make it shallower, I'm expecting that to go up, simply because they are inversely proportional. And similarly, right? And if I make it steeper, linear flow parameter goes down. I'm gonna set it to this part here. And also the location of this vertical line, left and right, will also determine the OGIP, right? So if I zoom in here, first things first, I'm selecting my time function to be material balance. I have also the option to select my phase that I want to do the interpretation on. In this case, this is dry gas, so I'm going to select gas. And this is contacted fluid in place that we determine. This is all anywhere in the software when we are talking the fluid in place is a contacted fluid in place, right? And this is my interpretation by the slope and the slope and the time to end of linear flow. And now it is time to decouple the different element of linear flow parameter, including permeability, XF, and NF. A critical parameter that goes into that is the number of fractures, right? How many fractures? This is an input parameter. When we plug this in, let's say these calculations that are grayed out, these are calculated. These parameters that are grayed out, these are calculated. So including the matrix permeability and fracture half length. So if I go ahead and instead of 127, I put 227, then my permeability is going to be lower, right? If I put 1, then it's going to be my permeability is going to be higher, 31, right? So just spend some time, get familiar with this one, and this interface is going to be repeated when we are dealing with a numerical RTA as well. So this is pretty much everything once we are dealing with the analytical RTA. And on the bottom, there's an empirical assumption. So this is everything after. Let me remove this one so make it less busy on the bottom. So if you want to add some decline curve analysis to the tail of these production data, especially after the time to end of linear flow, you can adjust this rate exponent and etc. It's a very simple decline on the data that tells you how you can adjust these lines attributes. Do we have any question? Okay, there's a question. When would you want to set the y-intercept as 0? This is I feel like, so there's a question in the chat. Yes, I totally agree with you. It doesn't make sense to force the data. It should be data telling us what's going on, not us making the data and torture the data, right? Ronald Hoare would say, if you torture the data, they're going to confess to anything. So I'm going to torture this data and force the data to go through the intercept. This option here is lock the intercept at the origin. Then I have only one capability to adjust the slope of the line, not the intercept, right? So that's a great question. We would let the data to tell us the story, not us making the data tell us the story that we would like to hear. So that's my answer to that question. If you don't have any question, I'm going to proceed with the slide deck and cover the numerical RTA for maybe 10-15 minutes. No question. Okay, let's proceed with the numerical RTA. This
I
is
have a quick question on the
please.
initial reservoir pressure. Sorry. What would you guys recommend for quick and easy? There's no flowback analysis, nothing like that. What would you recommend for
Okay, so
just staying within Whitson and picking that initial reservoir pressure that you think is like good enough?
yeah, so that's a great question. In the absence of any additional information on the flowback, how would you pick your initial pressure? If I want to quickly get back to this bottom hole pressure option here that we have, you see in the bottom hole pressure module, we have an option that says estimate initial reservoir pressure. I'm going to leave it here, but I recommend you to take a look at the manual and say how does it work. So if you click on this one, it's kind of nodal analysis that demonstrate the first tens of the data and try to fit an IPR curve that with the IPR curve information on the y-axis, it's the initial reservoir pressure. So if we only analyze the first chunk of the data, the y-intercept should be your initial reservoir pressure. So that's our alternative solution. But take a look at this in the manual and you will definitely find out some more information. How could you, so there's another question, how could you know the performance of each stage or each cluster? With this high level analysis that we do, we definitely don't have any idea. So this is treating all the fractures to be identical and treating, because we are measuring the rate on the surface, and in order to be able to identify the performance of each stage or each cluster, you need definitely much more extra tool like put in the tracer and analyze the tracer flowback data, or maybe production logging tools is also a great tool that say people do that in order to understand which part of the segment of the reservoir is underestimated, overestimated, understimulated, or overstimulated. So we definitely need some additional tools to help us identify the individual cluster performance efficiencies. So let's proceed with the numerical RTA. It's the second part of the talk. And let's say the component that we need for the numerical RTA is definitely PVT production data. And that's what we did with the classical RTA. But we also need relative permeability, right? The relative permeability is barely measured for unconventional reservoir, but there are some workflow around how to get comfortable with the uncertain parameters like relative permeability. And in the classical RTA, this is the model. These are some of the main assumptions that we needed to, one, the single phase constant PVT, etc. But in reality, it's a multi-phase flow. The bottom hole pressure is not constant rate. It's everything variable. Is all of these are violated. It's not single phase, not constant PVT, it's not constant rate, it's not infinite acting. So let's see some of the examples. If I'm flowing the well above saturation pressure, and by the time it, so for this data, if I'm lucky enough to collect like 3 months of data, 6 months of the data on the rate normalized pressure versus the square root of time, going to demonstrate the straight line. I'm going to use the slope of the straight line to identify linear flow parameter. By the time I proceed with pressure, bottom hole pressure, dropping below saturation pressure, they're going to be different slope here, right? And one reason what it could be bending upward once we are dropping below saturation pressure, despite the fact that I'm in infinite acting, because we saw in the classical RTA, this only happened once we are hitting some boundaries. Well, this happened, this artifact of dropping below saturation point. And one potential reason is once we are dropping below saturation pressure, gas evolve out of the solution and occupy some porous space, drop relative permeability of the oil, and this cause under the same pressure drawdown, we are going to produce less oil, right? So therefore it's bending upward. So it could be manifestation of going below bubble point, but it could be wrongly interpreted as a T end of linear flow, which comes with some consequences. These are some of the consequences that if we interpret the time to end of linear flow wrongly, that coincidence with the time that the pressure drop below saturation point, so we can wrongly have this conclusion. So again, fundamental assumptions is very similar to classical RTA. This is the geometry that we are trying to solve. Again, some limitation with the classical RTA. This is for a constant flowing bottom hole pressure, and I plotted delta P versus Q versus some sort of time function to account for not constant rate. And if the well is infinite acting, the slope gonna tell me the linear flow parameter. Right. So, but for the same well, still in infinite acting, and instead of producing at a constant flowing bottom hole pressure, let's impose this boundary condition, a step change of the pressure, not even transitional, a step change of the pressure. I'm going to plot these data on the specialized plot and see anytime there's a sudden change, as I demonstrated on the software, there's a different slope on these data. So these part of the data attribute to this period of time. So it will definitely take time for this data to settle on the right slope. So if we have many of these interruption and hiccup, which is not in very smooth, but a step change, we're going to definitely have hard time in the classical RTA. Is my real slope with this guy, or my real slope is going to be steeper, or my real slope going to be this one. So these are the challenges with the classical RTA. Next, if we drop below saturation pressure. So two wells behaving are in the infinite acting. One, the bottom hole pressure drop below saturation point at close to 300 days, the other one at 140 days. And I'm going to plot the corresponding data on the specialized plot, it'll be over Q versus square root of time. And for both of them, they show a kind of T end of linear flow behavior, despite the fact that I know I generated this data myself in a numerical simulation, and I know that they are still in the transient flow. But the way the multi-phase flow effect is once going below saturation point is we're gonna show demonstration of the end of linear flow. So with the numerical RTA, it's developed to address those questions, especially with the variable operating condition. Everything is real time. Don't need to be worried about if it is in the superposition time function or etc. And account for the multi-phase flow is definitely pressure dependent PVT, so it's not for gas, also for multi-phase flow. So this is the beauty of numerical simulation, and also some complex reservoir response. With the complex reservoir response in the classical RTA, we didn't focus on the fracture itself, right? The fracture can also be dynamic. The proton can crash on themselves, but can crash on themselves. And with the numerical RTA, we can also adjust the fracture properties along with the formation matrix properties as well. So this workflow was generated by these two gentlemen in this RTA. I highly recommend you guys to take a look at this paper. We make sure to just send it through our follow-up meeting. But these two gentlemen, ever since they developed, people fell in love with that, because at the time before this method was developed, it was a huge effort in the industry to adjust classical RTA somehow to be able to adopt them so they can be accounted for multi-phase flow effect. So it got really complicated, but at the same time, despite the fact that there has been some improvements, but still there was a lot of limitation when it comes to the multi-phase effect, multi-phase flow effect, especially dealing with what time function is the best can be used for similar for our analysis. So they say, okay, we're going to take advantage of numerical simulation, and we're going to still be in the same world of linear flow parameter and OIP, but this time with the linear flow parameter. So these are some of the key conclusions out of their paper. So what I mentioned, so first of all, I'm going to highlight that for this conclusion to be valid, we need to make sure that fluid initialization, the PVT part, is consistent between the two wells. Relative permeability relation is also consistent. If we run the two wells with the same bottom hole pressure profile, right? Both above and below pressure, saturation pressure. So if we use numerical simulation and use the same bottom hole pressure for the two well, Now, let's go through this conclusion. If we keep the linear flow parameter, we know the component that goes into the linear flow parameter, NF, permeability, H, square root of permeability, right? If we somehow distribute this parameter, but in such a way that linear flow parameter for well 1 and well 2 are the same, then those two wells gonna be similar performance during infinite acting behavior. Conclusion number 2, somehow we know that linear flow parameter XF, H, and F goes into those. And for OIP also there's the XF, there's lateral length, there's the thickness, porosity, etc. If we distribute those parameters, but what we're gonna keep between the two wells the same, linear flow parameter divided by OIP. If we do so, if this is the common parameter between the two wells, then the GOR and water cut for the two wells will be identical both during infinite acting and bonded dominated flow. And lastly, but also the most important part, because we're gonna settle on linear flow parameter and OIP for our well, is if we keep linear flow parameter and OIP the same for the two well, they're gonna behave identical during entire production life of the well. This is amazing. So I'm gonna show you some of these. So for these two wells, 3 wells, basically case study that we did in a numerical simulation, we kept linear flow parameter the same. And what we observed during the infinite acting period, they behave the same, identical. During bonded dominated flow, they behave differently because OIP was not set to be the same for both of them. Next, we kept LFV divided by OIP for 3 cases, the same. The rate are totally different, the Q, but look at the GOR. They line thickness difference. They're the same, both during the transient and during bonded dominated. And lastly, we keep linear flow parameter and OIP, they will behave identical. This is the premise of the pillar of their the papers based on linear flow parameter and OIP. We are taking advantage of numerical simulation in such a way, I'm going to present in a couple of slides here, but in such a way that still we are in the domain of linear flow parameter and OIP. Let's stick with this equation one more time to just make some of these points more clear for you. So we are familiar with this one, linear flow parameter is this one. Therefore, this is going to be an equation that I'm dealing with. So if we have 2 wells, it's going to be my equation for well number 1, going to be my equation for well number 2. If I divide them by each other, right? Because we are running again, fluid initialization is the same, therefore some of these PBT will cancel out from numerator and denominator, and also the bottom hole pressure profile is the same, therefore I can easily cancel the bottom hole pressure as well. And what I left off is Q2 divided by Q1 is linear flow parameter ratio. So if I keep linear flow parameter between two wells the same, the rate gonna be the same. What the conclusion from. Still, they are using the understanding and takeaways from classical RTA, what demonstrate those concepts using numerical simulation. So let's see what's their workflow. So based on this, that if the rate ratio is equal to linear flow parameter ratio. So what I'm gonna do here is create a numerical simulation model, which is infinite acting entire life, entire production history. And I'm gonna use the same PVT in my actual well because I'm very confident I can get my PVT from actual well. And with relative permeability, I have no idea, but there are some workaround to get them. But I can impose the bottom hole pressure profile of my actual well and use that profile to my reservoir model, which I know the linear flow parameter already, right? I'm gonna do that. And what I'm gonna do, I'm gonna run the infinite acting model with the predefined PWF from actual well, and I'm gonna generate this rate profile. So this is the first couple of steps that we need to take. I'm gonna calculate the ratio between the actual measured oil rate and infinite acting model oil rate. So this is simply rate divided by, this is what I generated from numerical simulation, this is what I measured. So if I do this based on this equation, I'm gonna get linear flow parameter ratio. But the good thing is that for my model, this model, I know what linear flow parameter I plugged in the numerical simulation. So if I do the rate ratio and I take, I calculate this rate ratio and I know my linear flow parameter ratio, the next step would be simply multiply the linear flow parameter from infinite acting model by the ratio, and I end up getting linear flow parameter for my model. It's very simple, huh? So, but we're going to use numerical simulation to generate these. Therefore, I'm not worried about any type of time function. I'm not worried about multi-phase flow effect. I'm not worried about anything. So this way, very simple, yet very rigorous, I can land on a correct linear flow parameter. In the next step, So I generated this model, this linear flow parameter versus time, but I know that during infinite acting, the ratio will stay constant. During boundary dominated flow, my data start to deviate simply because my actual well data start to hit the boundaries, right? So once my actual well data start to hit the boundary, I see it's curving downward. So my flow regime identification based on Bowie diagnostic plot is if my line stay flat, I'm in infinite acting. If my line stay to deviate and bend downwards, I'm in a boundary dominated flow. It's a flow regime identification, but has been done differently. And third, so the magnitude of this, the linear flow parameter, clearly it's a rate ratio. I have linear flow parameter for my simulated model, therefore I can calculate it from my actual one. So far, my linear flow parameter is known. What I'm gonna do, I'm gonna put aside my actual well data. Now I'm gonna go only to simulation, right? Now, so far I have a very large numerical simulation model that I generated the rate with the PWF from the actual well. Now I'm gonna truncate the end of linear flow parameter, reduce the size, and repeat all the steps from 1 to 4. So if I start with a large model still, if I start to truncate the end of linear flow, this is the another stem that I get. If I truncate furthermore, another stem, truncate furthermore, another stem, truncate furthermore, another stem. And we're going to generate these couple of stems from numerical simulation. And what we're going to do, we're going to superimpose the actual data based on these stems. And we're going to find at what time, when I start to truncate the edge of my reservoir, my actual data and my simulated data will be consistently close together. I'm going to pick that one as my original oil in place, as simple as that. This is the premise of using numerical RTA, using simply by creating only 5 simulation model. You can generate as many as you wish, but landing on linear flow parameter and OYP. And the beauty is we can do flow regime identification, infinite acting boundary dominated flow, and the flat line indicate the transient linear flow, but it bend over its boundary dominated flow. We can also land on linear flow parameter and original oil in place. It's very consistent with the classical RTA, but instead of dealing with the slope and in time to end of linear flow, we're still dealing with the time to end of linear flow, but in different representation. It's still the same fundamental everything. A big component that goes into that is the relative permeability. These are the cheat sheet that is also in the manual. I highly recommend you, just for the interest of time, I wouldn't cover this much during this slide deck, but in the software demonstration, I try to show you how you may adjust some of these parameters, because relative permeability at the end of the day is uncertain parameter, but there are definitely some workaround how to be confident about those numbers. And this is also the cheat sheet for oil and for water cut. And so far we covered this one, We say the contrast, the difference, the strengths, and the beauty of some of them against each other. Still, we need to do both of them. But sometimes if we are dealing with a complex phase behavior, definitely numerical RTA win. And no wonder if the linear flow parameter that we get from both of them are different. Usually the numerical is higher because it accounts for all the physics. Remember, in the equation that I presented to you, all the PVT properties are estimated at initial reservoir pressure, while we know that they are dynamically changing as the pressure drop. However, the numerical RTA take account for those, as typically this is the directionality of linear flow parameter. Do we have any question?
Yes, I was just wondering, and thank you very much for this session again. That is the 5th step of the Bowie workflow. You have to repeat step 1 and 2.
Yes.
Does this go into an iterative step? Because
No,
I'm wondering
yeah.
if you would have more complex boundaries.
Yes.
Say constant pressure and all sort of, maybe a faulted reservoir, not just only the fractures that are acting, but you also have faults. And how much work is that in that last part to be able to get all right?
Well, that's a good question, but I'm gonna revisit one of the main assumptions that goes into that. This is valid for 1D model, right? For some complex model, if you have some different boundaries, for instance, like all the geometries that I presented in the couple of slides back on transition from one flow regime to another flow regime. For instance, assume that the well is completed in unbounded. This is the first well in the green fields, is unbounded well. we are assuming that there's gonna be some contribution from beyond tip of the fracture, but let's see how our assumption is to true reality. So if you are in the 200 and below nanodarcy, we can safely, very safely assume that the contribution from beyond tip of fracture is negligible. So still, the assumption of 1D model and no flow from beyond tip of fracture is valid. But if we are in the macrodarcy range permeability, there's going to be definitely some contribution from beyond tip of the fracture. So when we do the analysis, the Bowie diagnostic plot will tell you the XF, which is higher than what XF that you design and you completed your wellbore with. Because the contribution from beyond the tip of fracture, Bowie will accommodate those contribution with extended XF beyond what is designed to be able to produce those extra contribution. So revisiting the assumptions is also a critical step. Hopefully I have addressed your question.
Yes.
But I'm open to discussion anytime after the course as well.
Okay.
You know how to find us, and send us a ticket and challenge us if we get back to you in 2 minutes.
All right.
So it's a claim that we made earlier, and I'm very committed to that as well.
Thanks.
Okay, no problem.
I have a question.
Yes, I see. Oh, please go ahead.
Yeah, with this technique, you are able to identify the linear flow from the fracture, linear flow regime from the fracture.
Yes.
What in case of you are drilling in a natural fracture reservoir and
Okay.
and somehow the well is crossing over a natural fracture, you are able to identify any kind of flow regime, or it's not possible?
That's a great question. With the natural fracture, the stuff that implemented not only in our software, but generally in any software, it doesn't account for the natural fracture as a distinct media. What it accounts for is say, okay, I'm assuming my reservoir is homogenized and it's gonna give you an average permeability. So if you have naturally fractured reservoir, which is classified as a natural fracture reservoir, by that I mean that classical PTA, two parallel line and deep and valley, and so that wouldn't be demonstrated in RTA, right? What RTA is gonna give you is a homogenized average representative permeability. So if you mix all the permeability from natural fracture and the matrix, mix them up, give you an average permeability. That's what it gives you.
I see. So here there is no way to identify kind of dual permeability or something like this, no? No. Okay, right.
Well, with that, if there is no other question, I guess we deserve maybe 10 minutes breaks. And what we will do at the end of the session, we are going to demonstrate on the two wells how we can do a classical RTA on the oil well and numerical RTA on both gas well and oil well. Okay, so see you in 10:26 CST time. Hopefully you enjoy your break. So far, I have another half an hour to go, and try to dedicate these to the software. So stay tuned. So far, 89 people still online. That's great. It's very impressive. So many people have interest in learning the RTS stuff. So far, I hope you enjoy it, and definitely, I guess I try to add some of the question on my hand, but I see my colleague, respected colleague Teja, is taking the lead to add us a lot of those. Thank you, Teja. And let's proceed and with the software. So everybody, could you please go to the software, back to the software. And for the second well, so we can do the numerical RTA on this dry gas, but I would rather do it on the oil well, because that one is a little bit more complicated with the PVT. So we're gonna do both analytical RTA and numerical RTA on the oil well. So you may access the well that we're gonna do the analysis either through this drop-down list here. You can go to the first well for kite, or you can go to the well, and if you have a long list of well, you can easily type it in here. And there are a lot of functionality with the filtering, searching, making group out of the wells, etc. So try to feel comfortable using all the functionality, especially you can easily get lost if you're dealing with more than 50 volts, and especially with a lot of weird name on the pad number, well location, etc. So grouping is really helpful. Filtering is really helpful. A lot of great functionality on the filtering as well. And so if you can go ahead, please, and select for kite well. And these are the same interface as we saw previously. Initial reservoir pressure is a little bit higher on this one for 6600. Underneath the PVT, the PVT is not initialized. So what I want you to please go ahead and edit this reservoir fluid composition, and automatically it is the 101st day of the production from the well is selected. You may shrink or expand the data a little bit to see how the GOR is performing, so you can see the long-term behavior of the well, but I'm gonna focus on the early time. So if I settle my initial GOR to where the line is automatically selected, it says the initial total GOR is 750, reservoir temperature 237, and initial reservoir pressure on this one. If you see the same value imported into your card, please go ahead and save it. And once you save it, this is automatically generating your phase envelope, right? With the initial pressure demonstrated here. If you gotta get an idea what's the fluid composition, you can click on this one, and this is the fluid composition for your well. Okay? When I close this and go to the PVT tab, on the PVT tab, you see all the PVT properties for both oil and gas in solution. Similarly, you can export it. You can do some advanced analytics on the PVT side. So the well is identified to be a black oil well, and with the saturation pressure 2875. All good. So with this one, I'm gonna go ahead and take a look at the production data before doing an analysis. So it's over 1,000 days of production data, which is actually great. So by only taking a look at this amount of data, you kind of say, oh, my well has now it's a boundary dominated flow. But we're going to see if RTA techniques, especially analytical and numerical, is telling us the same story or not. So this is the flowing bottom hole pressure. This is the production data. And in the analytical RTA, the same interface, but this time, because the primary phase for interpretation is selected to be oil phase, so I'm going to stick for that one. But you can either go to the hydrocarbon phase and do the analysis. But on the hydrocarbon, you can also do the total reservoir fluid. With the total reservoir fluid is basically sum all the fluid stream, oil and gas on water. And with the water, you may argue, is it the production water from the fracturing operation, or if it is a reservoir water? So it could be all sort of uncertainty there. Well, for the time being, I'm just interested in selecting oil to be my primary phase, and these are the dashboard again for the same four plot. For the flow regime identification, I may start with the real time and see and include the unit slope as well as the half slope. So this is the how noisy the data can get using the real time. And if I select the also half a slope line. So the early time, if I maximize this one, so it's a clear indication of the transient linear flow for the early point, and it goes it's just presenting the data are presenting as the unit slope at the later life of the well. And now for the analysis itself, I'm gonna switch back to material balance time function, and simply I can adjust this line, grab the end of the line and adjust the parameters, and or select on the auto feed and say it as the initial start, and I'm gonna do the interpretation. Very interestingly, I'm gonna highlight so one point here. So the software, the way it is program, you will be able to deselect what portion of this data are undersaturated, what portion of them is saturated. So double clicking on the saturated part, so you're gonna remove the saturated part. But very interestingly, when I superimpose this saturated part, I can clearly see the artifact of dropping below saturation point as the time to end of linear flow. So if I use my interpretation as this to be the end of linear flow, I may be in some wrong interpretation. So therefore, I would rather focus on the slope only, not to the time to end of linear flow. So I'm not doing any interpretation for the original fluid in place. So I'm gonna include this one again. And if let's see what we're gonna get if we use different linear superposition. I'm assuming this part of the data that shows this upward character gonna lie for a little bit longer on the straight line. So and apparently for once it's dropped below saturation point, it is really pronounced here. So focus on the just using this chunk of the data to be my interpretation for the linear flow parameter. This is what I'm gonna get from the linear flow parameter with the time to end of linear flow, as I said, because it's significantly multi-phase flow there, so there's less applicability for the time to end of linear flow. And once we are comfortable with our interpretation, both the slope and to end of linear flow, then we can decouple the information over here as well. So with the let's see. So there's apparently all the most of the assumptions for the classical RTA fails here. Therefore, we're going to rely on the numerical RTA and see what we can get out of that. So if you go to the numerical RTA, in terms of the interface, this gonna let me introduce you to the interface. It's very similar to what we saw in the classical RTA in terms of the phase that we're gonna use for interpretation, linear flow parameter. These are blank because I didn't run any calculation. So let's go ahead and run this calculation. And once we run the calculation, these are the dashboard that we're gonna get. So let me walk you through this dashboard a little bit here. So on the top, this is the cumulative linear flow parameter. You may argue, what's the cumulative linear flow parameter? So in a slide deck, what I presented to you will say, well, the ratio of QOM is correspond to the ratio of linear flow parameter, right? It could be either Q in instantaneous Q or could be alternatively, the ratio could be cumulative production. So I can toggle between the two. Somehow this one is integral of this one. So you remember in the classical RTA, we had different tools. One is derivative, the other one is integral. So it's a very similar tool here, integral as well. So this cumulative is very similar to application of integral. So if I deselect this one, you say my data, especially dealing with the noisy data, is all over the place. So I'm gonna go back to the cumulative and see how does it look like. On the top, to the right of that, it says a GOR plot. So for GOR is significantly depend on the input relative permeability. And I'm gonna show you where you can input relative permeability. If you scroll down on your this panel, left panel, you'll see on the bottom, there is an edit button and you can view your relative permeability. The very interesting part about this is you can not only adjust the relative permeability for the matrix, but you can also adjust it for the fracture as well. So this is the relative permeability and this is the edit relative permeability. So you see for the fracture, you can input this information. These are a defaulted relative permeability parameter, not necessarily is correct. And I'm gonna show you how you may adjust some of these parameters to get a better match on the cumulative oil and gas and water. So you may get familiar. So you can, once you're comfortable with your well, you can save it and you can call the relative permeability from here for other wells. The general rule of thumb is sometimes we have seen people go really push these numbers to non-unrealistic values. What is unrealistic value? There is no threshold and no textbook definition for unrealistic value. It's just coming from your guts. But if you keep a relative permeability set for your analysis, make sure almost the same numbers will be used for the rest of the wells, at least in that region, right? That's the main important part here. So not for one well, use extremely low value for relative permeability, and for other well, use extremely different numbers for relative permeability. So that's the key to keep in mind. And let's take a look at this this linear flow parameter. So the software automatically do all the calculation for us. So you see this is these are the different type curve stem. So if I hover my mouse on one of these type curve, you see the linear flow parameter is close to 42,000. OIP is 196 MSTB. If I go to another stem, my linear flow parameter stayed the same, 4192, right? 41,920, but my OIP start to get higher. So this is the steps that we took in the numerical RTA. So the first part of interpretation, if to settle this line where we see almost a horizontal line. These data are clean, kind of clean data set, and you may argue this really depends, or you may ask, okay, where do I put my horizontal line? Do I honor the first chunk of data? Do I honor this peak, or do I honor this later part of the data? So it really depends on how do you feel comfortable with the data, right? If, for instance, there are some operational issue going on here, and you see this is not the reservoir effect, what really goes into this calculation is the bottom hole pressure calculator. So if my bottom hole pressure are erroneous, like this is my bottom hole pressure that goes into the calculation. So something happened, some intervention happened. This is the artifact of the intervention. It's not the real reservoir effect. So you may say, well, this chunk of the data is not trustworthy, so I'm gonna ignore that. This is the true reservoir behavior. So I'm gonna pick this part of the line to be my true interpretation. So we also have the capability. So this part of the software is very similar to analytical RTA. You have linear flow parameter, you have contacted OIP, and here because it is at the end of the day it's a numerical simulation, you have some options for the grid refinement, which is set to a different level. To start with, always start with a low to get where in the solution space you are sitting. Once you are getting to the solution space, then you may switch to more resolution on your grid block. Here, you can also select how many type here would you like to see on this one. So in this case, I'm gonna see maybe it's a little bit sparsely. So I'm gonna have more resolution on my type here. I'm gonna go ahead and select 10 and click on run to have 10 type curve showing up on my curve, and I can see that there's a slight decline on my actual data. So you may argue, well, you also have the capability to put in your number here as well. So if I get like 800, if my type curve doesn't show exactly the match that I'm interested in, you may go ahead and put 800. So you see my data is a decline curve, decline trend in the actual production data where I try to match my data. And so I can argue this 400 first days is actually the infinite acting. The second part is a boundary dominated. I see a question about the relative permeability. Okay, so do we have any idea about the relative permeability? The answer is, well, we don't collect those information. We don't do any relative permeability experiment. If you see you're lucky, share it with us. So my point is that there are very slight chance of people going to the lab and getting a chunk of core and asking the lab to measure the relative permeability. It's usually a part of history matching procedure. What do I mean by part of history matching procedure? I take a look at my OIP, my GOR profile, and also we have a cheat sheet here, which I recommend to take a look at. It's also in the manual and also included in the software. So if you see some of these trends, you may adjust these parameters accordingly to get a good point, to get a good history on the GOR. So, but how do we adjust relative permeability? Simply, we take a look at the GOR profile and water-ore ratio. So you can see, I can clearly see my data is, my model is under predicting the water rate. So what I'm gonna go ahead right now to address your question, I'm gonna scroll down, I'm gonna select this one. I'm gonna reduce the critical water saturation from 20 to 10 to see the immediate impact on how I'm getting the history match on the water cut. So when I click on that one, so I'm aware that the early part of this data is definitely not the true reservoir because we are not modeling injection into during this process. So this could be the flashback production, but this could be the true reservoir behavior. So I adjusted relative permeability, and once I adjust any of these parameters and I get an exclamation mark, then I have to go ahead and rerun my simulation model to get the latest version based on my input. So if I click on that one, run, and let get populated. This information, you see, my GOR is very in line. I'm very comfortable with this one. And look at my water-ore ratio, right? So there could be other way. So I'm gonna just to show you that is not unique like anything else in the realm of numerical simulation. We're gonna suffer from non-uniqueness. I'm gonna put it back on 20, and in a step, I'm gonna bump it up a little bit. So I have to let relative permeability to water a little bit higher. So instead of 2, I may go ahead and put it 1.5 and save it. I'm gonna see if I get the similar behavior here or not. So run it one more time. Maybe to save some time, I can also go with a 5 and run it instead of creating 10 type curve. I'm gonna create only 5 type curve. So this is what I okay. So sometimes you put it back. So if you push the relative permeability to some uncharted territory, it's inherently we don't within a numerical simulation. We should be aware that because everything is solved numerically, there's going to be some convergence, or there's going to be something around that. So I'm going to take a look at my water and say, well, it didn't have the same impact as the adjusting the critical water saturation. So with this one, not only I can look at the cumulative production, but also I can look at the individual rate profile to see how the rate profile look like. And there are some adjustments for the time stepping. With the time stepping, you can adjust it to be a smart custom all. When you are selecting all the data point will be selected for numerical simulation. With a custom, you can select, okay, how often do you want your numerical simulation to account for the to basically run the simulation at. And lastly, a smart is my preferred one when I'm selected my final reservoir simulation. So on the GR side, also you see how very well, I mean, very comfortable with this one as well. And now, if this is the what we are getting out of this one, linear flow parameter is 43,300, and I'm gonna compare this one with the analytical RTA. I don't need to go to the analytical RTA and see. I can easily go to this icon here, and there information for the linear flow parameter analytical RTA is shown here. So you see the relative permeability play important role here. The cleanness of the data is also important. At the end of the day, we are running all these numerical RTA based on the bottom hole pressure profile. In case the bottom hole pressure profile are showing some noisy data, then we need to be able to maybe smooth them. This functionality is available in Whitson software. So just go to the certificate. A good chunk of those information is included there. And there is another parameter that I want to talk about is this gamma parameter function here. So this gamma, it is about the manual. If you want to access the manual, for instance, you have some question about the relative permeability here, you can easily click on this user manual. And if you are in the user manual, all this information are provided related to this numerical RTA with the table of content to the right of that. So all of this information are available to you. And something that okay, so these are some of the behavior, for instance, that we have observed. If you are dealing with a finite conductivity, what would be the signature on the GOR, right? How would relative permeability impact those? These are pretty much what I presented in the slide deck. And so very useful information. And the data that's included as the, for instance, some of the example that the what are important is in the diagnostic, in the Bowie diagnostic plot. Is it do we need to set our horizontal line to the IP, or is it more the tail part of the data that is important to us? So spend some time, just get familiar with this one. And these are some of the examples that I went through. And so especially when it comes to the fracture itself, FCD, maybe I can quickly show a couple of slides on you on the what would be the importance of finite conductivity fracture. So these are the evidence of low FCD. So we talked about that, the intercept that we get on the y-axis. If we are under saturated pressure, then we are expecting the GOR to linearly increase, and also on the linear flow parameter. So it takes a little bit of time for the data to stabilize on the horizontal line before it goes on the decline. There was a very great question about the application of PTA in coupled with RTA. So especially those information are going to be very useful during the build-up, because the build-up is more pronouncedly impacted by the fracture rather than the matrix. So if the model and the data are, especially we need to have the bottom hole gauges for this, right? Because during the build-up, we don't know dynamically what's happening in the wellbore. Therefore, the bottom hole gauges can definitely shed much more light on the analysis itself. So these are some of the observations on the classical RTA. There was a couple of questions about, now that we have numerical RTA, why should we do classical RTA? And still, there are some strengths. There's complementary to each other. It's all the matters of looking at the data from different lenses and from different angle. So once you are checking your data and your story that's using the tool of numerical RTA, as if it is consistent with the analytical RTA, then yeah, this is a second verification that your interpretation is correct. So with the pressure dependent permeability, again, or how does it demonstrate itself on the, I try to include this slide. I didn't go through the course, this slide during the course, but you definitely have access. You already have access to this through the manual, so you should be able to find all of this information on how the linear flow parameter and OIP will be analyzed if we are dealing with the pressure dependent permeability, etc. Right. So with that, I want to take a quick moment, maybe a couple of minutes, to quickly walk you through the last well that we have here as a crow well. And this crow well, okay, so I forgot to mention about this gamma parameter. So this gamma parameter, you can find some information in the manual, but it's basically what it does is correlate the permeability to the initial permeability based on the pressure. So on the y-axis, you have the permeability ratio, which is current permeability divided by initial reservoir permeability plotted versus pressure. So if it is set to 0, it means that it is exponential function. Exponential of 0 is equal to 1. So basically, the ratio is 1. But if I started, the unit is E minus 4. So if I started with 1, I want to show you. So if your initial pressure is 5,000, right? If your initial pressure is 5,500 and your bottom hole pressure is 1,000, this is the permeability loss that you will experience at the interface of the wellbore. So almost 40% permeability loss at the interface, indicating as if you are dealing with 100 millidarcy rock permeability with the inclusion of the gamma pressure dependent permeability, if your bottom hole pressure drops to 1000 psi, your permeability by that time going to be 60 millidarcy. Let's see, go aggressive on that, and maybe 4. So let's say how drastically the permeability dropped to 0.2. So 80% loss in the permeability, quite significant, huh? So just remember, so you may torture your data to may go all the way to 6, but 6 is almost you're losing all of the permeability. So it is telling you some information about how you may have a drawdown management strategy to consider some of these effects, right? So I'm gonna keep it 6 for now, and for the fracture, I'm gonna also keep it 6. Maybe I start with 0 to see the impact of those on the Bowie diagnostic plot. So again, starting with the PBT, this is my GOR profile, and I'm gonna click save, and my PBT is generated, my production data, my analytical RTA. Let's start right from the numerical RTA, right? And if you click on run, and So this is the behavior of the data. So this is something that was also mentioned in the manual. So where do you want to really sit you may argue, okay, this is my interpretation. I don't know. I don't want to basically history map the early part of the data. But you may also argue it could be another scenario where both of them are 6. Let's see what we get out of the 6. Now we say, well, maybe this is a more realistic scenario with the gamma of 6 for both matrix and fracture. The GOR is definitely doesn't look to my favorite. Therefore, I'm gonna adjust the relative permeability a little bit. So my model is under predicting the data. Therefore, maybe I go ahead and adjust the critical gas saturation. I don't want to drop it to 0 just for the demonstration purpose. I'm gonna make it 0. That's really 0. Is it very consistent to your guts, or do you believe 0? That's something I can't judge. But just for this case, I'm gonna show what would happen if we set critical gas saturation to 0. So maybe I need to include the 5 smaller model. Sometimes, again, because this is a numerical simulation, so I have to select some of these. Still, I can adjust my relative permeability to gas a little bit higher. So, and maybe this is good enough for now. And if you're comfortable, there are a lot of capabilities to export this information to more sophisticated tool, which is the numerical tool. And if I click yes, and then everything will be automatically populated underneath well and reservoir card here. So all the information on gamma, etc. And you see one of the main assumption or key assumption, fundamental assumption was there's no flow from beyond tip of the fracture. So these are already selected to be selected to maintain the except doesn't go the reservoir doesn't go behind except. So these are the two tools, analytical and numerical RTA. There's another component to the analytical, which is fractional RTA. I didn't want to cover that because there was too much content on that RTA. It's going to be RTA loaded. 80% is still on as success for me. I truly appreciate your time. I hope you learned something new here. And definitely would be love to follow up with you after the course. I see some of the question has not been yet addressed. We definitely make sure you will address all of the question. If some of the question has not been addressed, make sure to reach out. We will be happy to set up a dedicated session with you and walk you through what we know about all of these tools. And hopefully you enjoy the course, and leave us some feedback. It's the first time I'm offering this course, so it's really your feedback going to be very constructive, and love to hear about your feedback. It's almost 11, Calgary time, and hope you will enjoy rest of your time.
Thanks so much, Hamid, and thank you to everyone who joined.
Thank you. Bye.
Have a great day.